Welcome class, this is Dr. Soto and I am going to do problem number 10 from section 2.7, the worksheet on section 2.7 on related rates. And the problem is as follows. I've already done the problem and I've already had the solution. In fact, it's already posted on Titanium, but in case you want to hear the explanation, this is what this is. And I've written it out because it is a really long problem, and if I wrote it out as I try to explain it, I think it'd take too long. But in any case, what's going on here is that we have water that's leaking out of an inverted conical tank. So here's our inverted conical tank. Here's the water that's coming out, and it says that it's leaking at a rate of 9,500 centimeters cubed per minute. We also know that the tank has a height of 6 meters, or as I wrote down, 600 centimeters. And the diameter at the top of the tank is 2 meters, or like I wrote down right here, it's also 200 centimeters. And then the question goes as follows. If the water level is rising, so right here, the water level is going up. If it's rising at 20 centimeters per minute, when the height of the tank is 2 meters, so notice it says it's 20 centimeters per minute when the height is 2 meters or 200 centimeters. What we like to know is at what rate is the water being pumped into the tank right here. This is our question. So water's coming in, water's leaking, and then the volume's increasing in this tank. So hopefully that helps you understand that there's more water coming in than going out. And so in fact, that's what I try next. So next I go with the rates. And so going with these rates over here, oh, sorry about that. Let me see if I can just move it up. All right, there you go. So we have, the water of what's leaking. And so I decided to label that as dLdt. That's the rate of the water that's coming out. And then there's water that's being poured into the tank, and so I call that dp dt. It's coming into the tank. And I'm going to let h be the height of the water in the tank. And then what makes this problem really difficult is there are more things changing. And so I asked the question, in this problem, what's changing? Well, if you notice, what's changing is the volume in the water. Since water's coming in here and water's coming out, the volume in the tank is exactly what's changing. And in fact, not only is the volume changing, but so is the radius of this little cone of water that's inside the tank. And so I wrote that down. The radius is changing. And so I'm going to let r be the radius of the top of the water that's in the tank. And then what I wrote a little bit lower is that the volume is also changing. So V is going to be the volume of this tank. Okay, so now I have everything that's changing in this problem. So again, going back to this picture, we've got water leaking out, water coming in, volume changing, radius changing, height is changing. And so what I need is a series of equations that puts this all together. And so here are my equations. So somehow I need to relate these variables. And so one of the easiest relationships is the volume of the water, because we know that the volume of a cone, if we look it up somewhere, it's 1/3 pi r squared times h, where r is the radius and h is the height of the cone. But what about these two other variables, the water that's being poured in and the water that's coming out? And so here we have to think a little bit further and notice that if you pay close attention, the volume that's in this tank depends on how much water is coming in and how much water is coming out. And in fact, I would say that the volume is the amount of water coming in, or the rate of water coming in, minus the rate of water leaking out. So the rate at which the volume is increasing in this tank depends on how much is coming in minus how much is coming out. And so here's our second equation. We actually won't need it right at the beginning. It actually ends up being a lot more helpful to us later on. So we'll focus on this volume here, 1/3 pi r squared h. And so what we need to do is find the derivative of the volume with respect to time. Since the volume is changing, we know we can take this derivative. And of course, notice that we are given that the height's given, but we're also going to need to know how the radius is changing, and that's quite a few variables. And it turns out there's an algebraic technique that allows us to get rid of those variables. And so what I would like you to see is that there's actually two cones in this picture. There's the big cone, the tank that's 600 centimeters high and 100 centimeters radius, and there's also the water inside the tank, and the height's changing and the radius is changing. And so since these two figures are similar, we know that they're proportional, and so we can set up a proportion. We can say that the radius over the height right here which should be the same proportion as the radius of the big tank over the height of the big tank. And so we get that this is 100, that r over h is 100 over 6, or just 1 over 6. And so what we'll see then is that, let me go on to the next page. And so what we have here is that then we have that the radius is 1/6 h. And hopefully you have this worksheet in front of you so you can kind of follow along. But what this allows us to do then, solving for r, is that now we know that r is h over 6. And in our formula, remember we had our formula for our volume, 1/3 pi r squared. I can replace the r here with h over 6. If I square the h, I get h squared. If I square the 6, I get 36. And then h squared times h is h cubed, and 3 times 36 is 108. And so now I have a really nice formula that I can use to take a derivative of. So we take the derivative of the volume with respect to time. It's just dv dt. Pi over 108 is a constant, so we leave that alone. The derivative of the h cubed, well, we take down the power of 3, we subtract 1 from the power 2, and then we just write the h dt because of course h depends on time and we just don't know how. And so when we simplify this expression, 3 goes into 3 ones, 3 goes into 108 36 times, so I can reduce the fraction. And now I have all the information I need, and now I can go ahead and start substituting things. And so here, is, if you can see, the volume, the height is 200 centimeters. That was given in the picture. If you go back to the original picture, you'll see I labeled that the height was 200 centimeters, and that the rate at which the height is changing is 20 at that particular point. And then when you plug this into your calculator, 200 squared times 20 is 800,000. 800,000 pi times 36, when we round off, is 69,813.17 centimeters cubed per minute. But if you notice, the problem asks you to round off to the nearest whole number, so I went ahead and rounded off to 69,813. Now, this is the amount, this is how much the volume in the tank is increasing, how the rate at which it's increasing. That wasn't our question. Remember that what we wanted to answer was what's the rate of the water being poured in? We wanted this. But there's this relationship in equation 2. We know that the rate at which the volume is increasing is equal to the rate at what's being poured minus the rate of what's leaking out. And so now we have numbers that we can substitute. We just found out that the rate at which the water is increasing, the volume of the water is increasing inside the tank, is 69,813 centimeters cubed per minute. And we were given that the volume of the water that's leaking is 9,500 centimeters cubed per minute. And so now I have a nice equation. I add 9,500 to both sides so that I can cancel this. And of course you see that I get that the rate at which the water is being pumped into the tank is 79,313 centimeters cubed per minute. So indeed, this problem is very long. It is difficult. It requires a lot of work. So this solution is actually already posted on Titanium. So feel free to download it, save it, print it out, whatever it is that helps. I try to write as much as possible, but in case you'd like to hear someone go over it, hopefully this explanation helps. If you have any questions, again, please feel free to email me. Good luck.